Thank you for the introduction. Okay, so let's get right to it with the key question, I think, of the whole series, which is, what is time? What is time? What do you think? You can shout.
Entropy increase.
Entropy increase. Okay, there you go. We have a physicist in the room. Anyone else? Something we made up. Yeah? Well, we go into the philosophy.
Time is what you measure with the clock.
Time is what you measure with the clock. An illusion. Okay. So I would say, maybe I will please also the physicist, I would say that time is a dimension. Right? And a dimension is a direction you can go in. And we're all familiar with 3 dimensions in our daily lives. The world around us is 3-dimensional. There's, you can add axes, perhaps if you remember from school, there's X, Y, and Z, and they're perpendicular to each other. And those are the 3 dimensions. And according to Einstein, time is the 4th dimension. And how that gets to be perpendicular to the other 3, that's something that I never understood. But that's okay, because I became a geologist. And what geologists did is we grabbed the X, Y, and Z, and we turned it upside down, and Z goes down into the Earth and is the axis that measures both the thickness of the rock layers as well as time. And I think this is something that to a non-geologist might be a bit of a surprise, but that is that geologists normally measure time in meters, in length scale, and not in time scale. In fact, I will try to show you today that in the 19th century, 18th and 19th century, and even in the early 20th century, we didn't really have good techniques to measure time in absolute terms, in years, and we already had a pretty good grip on geological time. So you don't actually need the clock to measure time. You can actually use the rocks without actually having an absolute age. The other thing is, geologists aren't really interested in the nature of time. To us, we don't really ask the philosophical question. Time isn't very important, actually, surprisingly. The thing that's very important for geologists is, and this has been a sort of epiphany in the 19th century, and it's a sort of a threshold concept for young students of geology, is the idea or the concept that with enough time, something that is very slow can lead to huge outcomes. Okay? And the other thing that's very important that you should learn as a geologist is that given time, the rare becomes probable, and given enough time, it becomes a certainty. And this is really what's important for a geologist in terms of time. This is a cartoon of Stephen Jay Gould, who you perhaps know. He's a very famous writer of science. He was particularly focused on biology and geology, natural sciences. And in his book, Time's Arrow, Time's Cycle, he described and he explained 2 metaphors for time. The first metaphor is time as an arrow. And time as an arrow basically describes time as a sequence of events which is directional and unique. Time cycle provides us with another kind of meaning to time, which is the lawfulness and the repeatability of and predictability of time. And to help you think about time as a cycle, what this means is that some processes, they keep repeating and they always have the same outcome. And that's time as a cycle. And throughout today, throughout this evening, I should say, I will make reference to both metaphors because both, of course, have a role in discussing geological time. Before we go there, I would like to talk about the discovery of deep time, to give you a historical context to how geologists have come to look at time. So Sigmund Freud, he once wrote that humanity has had to endure at the hands of science 3 great outrages. The first one was at the hands of Copernicus. Copernicus basically took humans from being in the center of the universe and displaced them to a mere planet that surrounded a star. And eventually, later on with Hubble, it turned out that that star was also not in the center of the universe, but just one in a multitude of stars, and that just greatly, vastly expanded the space scale of the universe and reduced humans to just a tiny speck or a pale blue dot in that vast space. The second outrage was, of course, the Darwinian removal of man, as they would say at the time, or humans, from being God's chosen creature to have dominion over the earth into a mere hairless primate. And the third one is illustrated on my slide with Oedipus, is Freud's own, which further removed humans from being this sort of supreme being, this special being, by questioning our rational nature. In the 1980s, Stephen Jay Gould again, in the same book, he mentioned that Freud forgot a 4th great outrage, which was actually the second, chronologically speaking. And that was the outrage of deep time. And just like Copernicus had vastly expanded the space scale where humans had to be found, geologists, and we will see there is not just one geologist that we can really name, but we will come to it. Perhaps we can settle on Hutton, which is a traditional hero of deep time in geology. What geologists in the 18th and 19th century did was they vastly expanded, not the space scale like Copernicus did, but the time scale of history of the Earth. And in doing so, humans who before had basically witnessed the whole of Earth history, except perhaps a first very brief creative prelude of 5 days, but everything other than that, Adam and Eve had witnessed, and everyone after them. Now suddenly they were confined to this sort of final scene in a much longer drama, which was Earth history. And that was, according to Stephen Jay Gould, the 4th great outrage. So, as I mentioned, the concept of deep time dates back to the 18th century, and on the right is Hutton, who was a geologist from the Scottish Enlightenment, friends with Benjamin Franklin and Adam Smith and all those very famous gentlemen from the 19th century. He's the traditional hero of deep time in geology. On the left, however, is Count Buffon, Georges Leclerc, who actually, at the same time, as well as other people who were involved in studying rocks at the time, together they actually realized that what they could see in the field, the processes and the slowness of the processes, as well as the vast thicknesses of the products of those processes in the ancient, required much more time than they were afforded by the knowledge at the time. And at the time, James Ussher, who was an archbishop of the Church of Ireland, he was a scholar. Afterward, he was quite mocked because he used the Old Testament to do this, but he was quite a feat at the time. He went all the way back, and he established that the earth had been formed on the eve of the 22nd of October, 4004, before our common era. And so that meant that the Earth was about, at the time of Hutton, the Earth was about 5,700 something years old. And Hutton, he There's this story in geology that all first-year students, I think, in geology learn, which is at this particular spot. This is in southeast Scotland, and it's a cape. You cannot see it from this perspective, and it's called Sicker Point. And the traditional myth is that Hutton was at Sicker Point looking at this outcrop like we're looking at the picture now, and he just had this epiphany, and he stared into the abyss of time, as it's often told. I think the story is likely apocryphal because Hutton didn't do significant field work until after he had given a lecture in Edinburgh, where he already presented his ideas about deep time. And so in essence, what he did is what we would nowadays call following the hypothetico-deductive method, right? He had a brilliant idea, no evidence whatsoever for it, and then he went out into the field in Scotland and he sought to prove it. And proven he did. The interesting thing about Hutton is, to come back to how did he have this idea, Hutton actually got his degree at Leiden University here in the Netherlands, where he got his degree with a dissertation on the circulation of blood in the human body. And then later on he went to Scotland, where he studied what we would nowadays call the hydrological cycle. So you're starting to see that there's a bunch of cyclicity in there, and Hutton, he lived in a farm, and he saw how the soil would be washed into the rivers and then taken out to sea. And he, unlike what we would think, most of these men, they were actually deeply religious. And so he thought that plants and animals, they served a single purpose, which was to make human life possible. And if all the soil would go out to the sea, then there would be no more soil, eventually no more land even, he wrote. And so there must be a mechanism whereby this can be replenished. And that mechanism, according to him, in his book Theory of the Earth, is the soil gets washed to the sea, it accumulates in the sea, and then it consolidates into hard rock, and then there is a slow, and this was critical, and I will come to the slow versus fast at the end of today's session. But there was a slow upheaval of the land, forming a new mountain, and then the whole process could restart. And the interesting thing is, Hutton did not foresee time as an arrow. Hutton thought that the Earth was a place of perpetual change, but with no direction. And as we will see, there were other geologists later on in the 19th century who followed the Newtonian theory, and they were in fact convinced that dinosaurs would return. So they thought that just the whole Earth was following this big cycle, which was in essence very, very similar to the scriptures with a return to paradise at the end of the great year. Early attempts to try to understand the rock record into an account of Earth history focused on the succession of the rock layers, of the strata. And geologists were convinced that certain rock types had been formed at certain times in Earth's past. And this is a cross-section through the Apennines, and the arrow at the top, just at the top of the mounts in the middle, points northward. And then from left to right, we see granite and gneisses and other crystalline rocks, rocks that are formed, consist of crystals that are interlocking. And toward the right, we see the strata, which they called secondary. So there were the primary strata, which were formed first. These were the granites. And then there were secondary strata, which were formed by the decay of the original strata. And Hutton, one of the biggest contributions of Hutton was to show that granites could not be older than the secondary strata. Hutton went out into the field. This is from an island in Scotland called the island of Arran on the west coast near Glasgow. And he saw how the granite, which consisted of these crystals, penetrated into the secondary strata in veins, which had evidence of having done that while being liquid, even picking up some of the secondary strata into them, and then had solidified. And so Hutton realized that these rocks, which were very old, they were actually younger than the secondary strata. And that's where he got his insight of deep time. Of course, Siccar Point is then used as the sort of, I think Siccar Point, I normally tell students Siccar Point is one of the holiest places in geology. And so it got its role, just like every city and every religion worth practicing needs to have its etiological myths, well, so does any science worth practicing. So I will indulge. What we see here on this picture is we see a variety of vertical strata at the bottom, which are sort of grayish. And these strata, they consist of sand and mud, hardened, hard rock. And these were deposited 420 million years ago. And the fossils they'll contain are fossils that we would position in something we call geologists the Silurian. And I will come to this later on. Then you see that there is a surface that separates, that cuts through these vertical layers. And then on top of it, there's these reddish layers, which themselves, they're also tilted. And the layers at the top, they are much younger. They are 370 million years old. And they do not contain fossils, but we can date them relatively by their geometrical position to other rocks as being Devonian, and we call them the Old Red Sandstone. And Hutton's great insight in looking at this was that the rocks that are vertically lying, he saw that they were marine rocks formed at the bottom of an ocean. And he thought that there must be some force, a vertical force, that pushed them upwards, and at doing that, it also put them vertically to make a mountain chain. This was eroded by weather, and that, in turn, produced new sediments, and the sediments were deposited next to these mountains. And those sediments are those reddish sediments here in this case, and those were then also themselves tilted. And he thought this must take enormous amounts of time. And not only that, he did not see this just for this particular cycle, but his greatest contribution was actually in putting down on paper that this was just one in an iteration of several of these cycles. Now you need to remember that at the time, every other person in science would tell geologists that they were crazy. Lord Kelvin calculated, of course they didn't know about radioactivity, but Lord Kelvin eventually calculated that the Earth could not be older than 100 million years. And for Hutton, as was true for Darwin, this was unacceptable because they could see that they needed more time. So very often you see on, what's the name of that show? The Big Bang Theory, physicists giving grief to geologists, but actually geologists got time right earlier than physicists. So there's a diagram just to illustrate you, if you weren't able to see from the picture, to see this concept, which is what we call an unconformity, which is a surface that separates rock layers representing a time gap in between. And in this case, we would call it an angular unconformity because the rocks are standing at an angle to each other. The time missing between the two, the Silurian and the Devonian, is about 50 million years, 50 million years. It's hardly an eternity. And Hutton, what he realized is that the deep time that he needed was not in the rocks, but in the gaps between the rocks. And that's where he found deep time. Hutton, near where he lived, had seen Hadrian's Wall after 1600 years. And he saw that the wall was practically intact as well. Not a great deal had happened to it in Northumberland. And so Hutton's imagination required time in quantities that was unknown of at that time. And he found that missing time, as I mentioned, in the unconformities. Stephen Jay Gould would later say that unconformities are palpable proof that the Earth does not decline but once into ruin. Instead, by following decay with uplift, time cycles the products of erosion in a series that shows, in Hutton's most famous words, no vestige of a beginning, no prospect of an end. Hutton's best friend at the time was John Playfair, who also wrote about Hutton's work. He would later describe the experience of being with Hutton later on in the field at Seeker Point as extraordinary, and he wrote in his own book, "The mind seemed to grow giddy by looking so far into the abyss of time." So how much time is deep time? So far I've been mentioning 470, 350, I'm talking about 50 million years as being hardly an eternity. How much time is deep time actually? So deep time, why is it called deep time? It was actually coined not by a geologist but by John McPhee, who's a creative writer at Princeton University, and he wrote a series of articles about geologists in the New Yorker magazine, and the first one came out in 1980 called Basin and Range. And it's in this article that John McPhee coined the term deep time. And the reason it's called deep time, it's, if we go back to the Cartesian axes, is because z, the time axis, as you go deeper and deeper through the layers of the Earth, time increases. And as you go deeper, you get deeper time. John McPhee wrote, "Numbers do not seem to work well with regard to deep time. Any number above a couple of thousand years, 50,000, 50 million, will with nearly equal effect awe the imagination to the point of paralysis." A good way of thinking about this is to consider that most people find it very, very difficult to understand the difference between a millionaire and a billionaire. If most people did, I think most people would be very upset and very angry at the existence of billionaires. And a couple of years ago, I watched a short clip on Twitter, which is shown here, in which a woman explained that it's our inability to deal with large numbers that makes us be unable to distinguish millionaires from billionaires. And she says that if you earn a pound every 10 seconds, it will take you 4 months to become a millionaire. But then you have to wait 310 years until you hit your first billion. So think about that. 1 pound, well, €1, and you will be a millionaire in 4 months, but then 310 years, so beyond our normal lives until you are a billionaire. For the geologists, this is the same thing. We talk with nonchalance about time. Most geologists will consider 1,000,000 years to be nothing. And we talk about it like, oh, it's just 1,000,000 years. But in fact, I think we do that with a certain amount of unease ourselves. I don't think even geologists quite appreciate the enormity of the numbers we're dealing with. We just get used to just shifting the scale. I guess it's like being an European using Fahrenheit in America. You can learn how to use it, but it will never quite be something that you dominate yourself. My favorite metaphor, it's actually a paraphrase, and it's a good example of when a paraphrase is better than the original, of John McPhee's work. And it's by Stephen Jay Gould again. And he says, "Consider the Earth's history as the old measure of the English yard, which was the distance from King Henry's nose to the tip of his outstretched hand." And John McPhee says, "One stroke of a nail file on his middle finger erases human history." Now, I would like to invite you to stretch without hitting your neighbor, to stretch your arm. This is a bit of embodied understanding. So the Earth's history starts at the tip of your nose, okay? Now, I'm going to turn my hand around. all the way from here, all the way to the first knuckles on my hands, the Earth existed and there was no life on Earth. Okay? All the way to this knuckle. It takes to the second knuckle for Pangea, which is the last supercontinent, to appear on Earth. The extinction of the dinosaurs with the big comets that impacted Earth 66 million years ago is the cuticle of your nails. And the whole of, and I cut my nails on purpose today, just for you, the whole of human history is, and you try to look from here, right? And actually we're cheating because we're already stealing some of the deep time, but all the way there, the tip is human history. And it's 0.03 millimeters, so 0.03 millimeters on your nail is since we've left Africa. And that's an order of magnitude smaller than a dust mite, which we can barely see with our naked eye. How humbling is that? The 6,000-year Earth, or young Earth as it's often called, was an almost wholly human Earth. And the deep time Earth was an Earth which was before Adam. It was a pre-human Earth. And this made quite a stir, of course, at the time. This is that outrage that Stephen Jay Gould was talking about. We should note, however, that Hutton, he was never able to find human fossils in deep time. He conceded that that was problematic, but he was convinced, as were many geologists back at the time, he was convinced that that was because the record was imperfect. Hutton and most of these geologists, they believed that the Earth was not a non-human Earth. They thought that even just the fact that they could find fossils of plants and animals meant that the good Lord had placed them there for the humans that were also there, but we just couldn't find the human fossils. And this has a bit of, there's been a bit of a whitewashing of history to try to put church against geology in the 18th and 19th century. But historians of science later on, they've analyzed the records, and the true story is actually much more nuanced. Most of these geologists, they were actually religious men, and they were not actually trying to disprove the Bible. They were not trying to disprove the existence of God. The only thing they wanted was two things: more time, and therefore a non-literal interpretation of the scriptures. And what they really wanted that distinguished them, that really represented a break with the past, is they did not want any supernatural forces to explain the phenomena. They wanted to be able to explain natural phenomena and Earth history just using things that they could see in action at present. An important aspect of this work and the discovery of deep time is that geologists realized that the Earth did not have a prehistory before humans, as in fact historians will tell you this nowadays. Before written word, everything is prehistory. But geologists will tell you, no, that's not prehistory, that's just Earth history. And geologists have learned since Hutton that Earth history has been quite eventful, and that it's possible to reconstruct Earth history in great detail. And this has been, I think, the contribution of geology to human knowledge. And geologists have done that using strata, which is another word for layers, rock layers, as a record of time. And the remarkable thing about Earth, compared to other planets we know, is that due to a combination of internal heat and movements of plates on its outer rigid layer, Earth has a remarkable capacity of actually recording the passage of time. Not all planets have this because things will not be preserved by being taken away from the area of the planet where they will be removed by Earth's or planetary surface processes. Let's go back to the old red sandstone, which, if you remember, was at the top of the unconformity at Siccar Point. This is a picture of the old red sandstone. In fact, it's not a sandstone at all, but let's forget that, in the island of Arran, where I also showed the granite of Hutton. The old red sandstone, and you can see the Netherlands popping up on that paleogeographic map here, was deposited south by rivers flowing south of a chain of mountains that geologists call the Caledonian Mountains. The Caledonian Mountains were formed when an ocean, which is in essence a predecessor of the Atlantic, closed, and in doing so, a chain of mountains was created by that impact generated by the closure of the ocean. And those Caledonian Mountains, if you wish, the remains of that can still be found in Appalachia in the eastern United States, Scottish Highlands, as well as Norway and Sweden. And these rivers, they flowed south from the Caledonian Mountains onto an ocean which we call the Rheic Ocean. As you can see, the Netherlands was on that southern margin. This ocean went all the way from southern England all the way to Russia. And this led to quite a big problem. Geologists working in the southern area of England called Devon, where you have the city of Exeter and Torquay, in that area, geologists found a rock that contained corals, which you can see on this picture, that they had never found before. These corals were more developed than corals that they knew, but they were also less developed than other corals that they knew. And the big breakthrough that occurred was when they realized that above the old red sandstone there were the more developed corals, and below the old red sandstone were the less developed corals. And this was quite a big breakthrough at the time, because what they realized was that unlike what they had thought, and that is namely that at certain moments in the history of Earth there was one rock type being formed, they realized that different places on Earth, of course, now it seems obvious for us, depending on the environments that are present in those places, have different rocks being formed with different fossils. And so they had this breakthrough of realizing that this rock, even though it's a limestone, a dark limestone with corals, was actually a time equivalent of the old red sandstone. So while in Devon, in southern England, there was a shallow tropical sea with corals, in Scotland there was these highland rivers with a lot of sediment being transported as the breakdown products of the mountain chain. And this allowed geologists to start understanding how to read time from the rock record. And so these old ideas that rock strata were global in nature and recorded the same events worldwide, they were abandoned, and geologists realized that they could work towards building what we now call a time scale by correlating, which is the word we would use, to establishing the relationships through time and space of all these rocks. So here's a famous a picture at the time, which is also a sort of metaphor that is very loved by geologists, which is to think about the rock record as a pile of books, each telling a story. And you can see the old red sandstone there at the bottom, and on top of it, these coal strata and the mountain limestones. Geologists in England, of course, it didn't take them long to see that if they came to South Limburg, they would see exactly the same coal, and in the Ruhr, and if they went to the United States, they would find it as well. And so they could correlate some of these rocks and use the fossils, and then they grouped those into the Carboniferous. In England, they had this rock layer at the top, which is called the New Red Sandstone. And then they looked to the Netherlands and to Germany, and they realized that here there were two sandstones with a limestone, a quite typical limestone in between, which is found in the Netherlands at Winterswijk. It's one of the few outcrops of rock that we have in our country. And so they realized that some things, they were similar across regions like Europe, and others were not, and they started to be able to correlate and to link this. And in this way, based on fossils, based on a directional history of Earth, so now they were moving to time as an arrow, they were able to construct the geological timescale. Here's the first geological map of a country, actually two countries, England and Wales, and it was produced by a canal surveyor called William Smith. He's also the first person who used the word stratigraphy to talk about what he was doing. He called these layers strata. And William Smith's main theoretical contribution, his contribution to geology, and what actually made mapping, geological mapping possible, was the recognition that the fossil record was very reliable, and namely the order of the assemblages. So he realized that it's not just the one fossil that you need to use, but you study the assemblage of fossils that occur in a layer, and they will invariably always be in the same order, even if the rock type is different. And in doing this, it actually made him bankrupt, and he ended, as many of these scientists at the time, he spent all his money trying to produce this map, and he actually never was acknowledged in his life for it. And if you're ever in London, you can go to Piccadilly, and at the Geological Society of London, behind the curtain, you can actually see the actual handmade map, and it's a thing of beauty. And this represented a big breakthrough because geologists were realizing that they could map the formations of rock, correlate them, and in this way, by combining the topography with the order of the rock layers, they could actually build a 3D picture of the rocks also in the subsurface. It's important to emphasize again, I've mentioned it before, but it's important to emphasize that this division of rocks into stratigraphic units was done before any method to determine the absolute age of rocks was available. Radioactivity was only discovered much later, and it took some time after that until Arthur Holmes, who was a young PhD student in London, realized that you could use the isotopes of uranium to determine the absolute date of rock layers. Now, the problem was also additional, and that is that, as Hutton mentioned already in the 18th century, most of these rocks, which are sedimentary, as we call them, they are the breakdown products from mountains, they have grains from a variety of origins, and so you cannot really measure anything. You cannot measure the time when it was formed. You would measure the time when the grains were formed, but the grains are much older than the rock that contains them. So you really need to have things like volcanic ash layers, which represent geological instants. There's this big eruption, it throws stuff into the air, they land and they form a layer which is basically instantaneous and contains something that you could measure primarily. Now, that's not often the case, and so they used fossils and they used the geometrical relationships between the rocks. There was a lot of arguing, particularly about the Devonian, for example, in fact, the Devonian is the outcome of a stalemate. They just gave up fighting and they said, okay, let's just call this the Devonian and make it a new interval in the rock record, which is the brown thing on the third column you see there at the top. But the interesting thing to know is they had no idea at the time how long it was. They could correlate it across the world, but how long it was, well, they had no idea. And for them, it didn't really matter because they were busy doing actually the correlation. And so they went through the layers, and you can see on the third column at the bottom, there's a unit layer called the Cambrian in green, which was named for Wales, which was where they found these rocks. And there's also the Devonian, named from Devon. In the middle rock column at the top, there's in blue the Jurassic, which was named after the Jura Mountains of France. If you go down on that column in red, there's the Permian, named for Perm in Russia. And so you see that they also figured that there were places in the world where the succession for a particular interval was more complete, was more representative of that interval in Earth history, and they would name it after that. Others, like the Carboniferous, which is at the bottom below the Permian in a sort of teal color, as well as to the left of it, in the first column, in green, the Cretaceous, were named for a certain rock which was very characteristic. This kind of seemed to go against that idea that at certain times in the past there were certain rocks, but indeed at certain times there were. And the Cretaceous, if you go to South Limburg again, you can see at Crete, and that's where the name comes from, Cretaceous. The geological timescale, what I'm showing you is the most recent iteration of the geological timescale, and it's constructed still nowadays. It's a work in progress, and it's constructed by integrating evidence. So there's evidence coming from the magnetic signal in rocks due to the field, magnetic field of the Earth, fossils, but indeed radiometric ages. And the important thing to realize is, so there's all those ages to the right side of each of those columns. And this is something that sometimes physicists and engineers I've spoken with, they just say, well, why don't you just use the numbers? But the point is, the rock record is not defined by the numbers. It's defined by actually the rocks. The numbers, they're actually subject to changing as the matter improves, or we have a better calibration of the isotopes, and the numbers will change. But any rock that contains a certain assemblage of fossils and has a certain geometrical relationship by underlying and overlying another rock is given a certain name, and we don't actually use absolute ages to give these names to the rocks. We've been talking about time in terms of numbers, but for geologists, time also has a qualitative nature. What kind of time is being recorded? And specifically, the question is, which is a question that biologists will recognize, particularly evolutionary biologists, and that is, how representative are the rocks of the time interval that they're supposed to represent? This question is particularly pertinent if you consider the incompleteness of the stratigraphic or the rock record. And I'm going to show you it's a modern iteration on a very old graph, and I will just first show you, and then I will try to explain as we go. So I'll just allow you to watch it. So the top bar shows in blue intervals where sediment is being deposited, red intervals in which sediment is being removed, and in gray, actual sediments that have been removed. So you can see, for example, that there's an interval that just consists of red and gray. That means that that interval in time, which is the x-axis, is time in years. In this particular numerical experiment, that particular interval is all gone. We have no record of it. There was record, but it's gone. Where is the record? That's the bar on the right. And you can see it. It goes up, and now down, and up, 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 down, 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 up, up, up. So you're seeing that sediment accumulates, and it's a little bit eroded, and accumulates a little bit eroded, and sometimes it's just more eroded. The wiggly line represents sea level. This is a particular experiment, numerical experiment for sea level fluctuations, and this is what would happen at the coast with the stratigraphic record that accumulates, and you'll see that it accumulates when it's rising the curve of the sea, and it's eroded when the sea is dropping. Now, the important thing to retain from this is the following. 60% of the time, the rock is accumulating, or the sediment. 40% of the time is being removed, but the upshot of this is that only 20% is actually preserved. And so the rock record, in a lot of places, is actually rather incomplete. And the funny thing is as follows. While the planetary time, while the Earth time, the age of the Earth, the whole of deep history, is beyond the imagination long, and the record is incomplete. What we find in the record when we look at it and we interpret it in terms of processes, what we end up finding is something which is very banal, very ordinary. This has been called by some stratigraphers as the strange ordinariness of the stratigraphic record. This picture is actually a collection of peels, and these are produced by gluing the surface of the sediment and then putting some gauze on top of it and then removing it. Shows a complete cross-section of a bar of sediment which was exposed during the delta works. This is the bar of Niltje-Jans. And what you see here are layers which are inclined from right to left. And the little dark layers, they're the clay layers, the fine-grained layers, and the beige, the yellowish beige layers, they're the sandy layers. And you can see that the thickness increases and decreases and increases and decreases. And what you're seeing there are fluctuations in the current velocity in the tidal channel. You're actually seeing each layer there representing 6 hours. And the fluctuations in thickness, these are the fluctuations due to the spring and neap tides. And so you're looking at bi-weekly things. And you can see this type of thing everywhere in the rock record. And they're supposed to represent, according to the fossils, much longer time intervals. And yet, we see windows, slivers of preservation of a few hours here and there. And so the question is, okay, so the rock record is incomplete, but it shows us just the daily processes. Well, the alternative view on this matter is a more catastrophistic, if you want, view of the matter. And that is to say, well, the rock record is so incomplete that it takes something phenomenally spectacular, like Hurricane Katrina shown here, to generate accumulation of sediment. Of course, Katrina will erode sediment somewhere, but it will erode so much sediment that it will be transported somewhere else and be deposited there. This view was championed by a geologist in the 1970s called Derek Ager, who said that the stratigraphic record, like the life of a soldier, is dominated by long periods of boredom, alternating with short periods of terror. And this is a picture from the trench war from World War I, which you probably never thought about World War I like this. You always think about the terror. But actually, most of World War I was bored soldiers, cold and wet, and just trying to spend their time in the trenches doing whatever they could do. And Derek Ager thought that the rock record, the stratigraphic record, would be like this. We're actually looking at slivers of the terror, and the daily stuff goes unnoticed because it's largely being eroded. This is actually inherited from the early days of geology, and it's a long-standing debate on whether the processes that we observe at present, in their present intensity, are actually responsible for everything we can see in the rock record, or whether catastrophes or revolutions, as geologists call them at the time of Hutton, are responsible for a significant part of the rock record. I think the answer is both. But what you can see also here is a cultural aspect in science, and that is namely that from the 70s, where you also had a lot of catastrophe movies. There was the Poseidon's Adventure and Earthquake and all those films. People were more primed to this, and this is the time where the brothers Alvarez, I think it's father and son, they discovered the comets that hit the Earth, and there was much more sort of propensity in geology to abandon these sort of slow processes acting for very long, but also consider short processes that induce a great terror on Earth and produce something in the rock record. And why is this important? It seems like an academic discussion. And this is Lyell, by the way, which is the champion of uniformitarianism, which is the doctrine that slow change over very long time intervals will lead to great change. I think this is particularly relevant now in the Anthropocene. So I was trained to be a uniformitarian, as I think most geologists will. Geologists, they are very careful with catastrophes because before you know it, we're going to be talking about Noah's flood. And so there's a sort of allergy that we have to catastrophes. But the problem is, if we truly believe that there is nothing we can do that will change the Earth, if only very slow change over very long will produce some change, then what do we make of the Anthropocene? And if we look at the data, we can see that even though we are 0.03 millimeters, we're just a tiny final scene in the history of this planet, we have produced gigantic effects on our planet in the short period. In fact, it's much worse than that because the 0.03 millimeters is since we left Africa, whereas most of what you're seeing there is since 2000 and 2000, probably since Al Gore. In fact, Al Gore warned us, and then we decided let's make it worse. I think the lesson from deep time should therefore not be that only slow change over very long periods of time can produce something. The lesson should be that short periods of terror are also possible, and I'm afraid to say that we are the short period of terror at the moment, producing great effects on our planet. The average species, invertebrate species, goes for about 10 million years. The average mammal goes for 1 million. And we should really consider that we are not going to be on Earth forever. Maybe there will be a new Homo, something else, not sapiens. Or maybe we will just go extinct and some other animal will become the dominant species on Earth. But it's very clear to any geologist that there will be a day after human life on Earth. And to me, the Anthropocene, what it means is that we should realize that we are the last species to arrive on Earth. Earth is not ours. In fact, despite all those outrages, we refuse to acknowledge that we are not the owners of the planet. And it forces us to reconcile ourselves with what is going to be the day after. What will it look like? What we will leave in the rock record? I thank you for your attention.